Okay, I'm going to try to do a short video, shorter than my long one, which is like 2 hours long, that discusses this stuff in a lot of detail. I'm trying to do a really short version of it, just to get the point across. If you need more explanation, look at the other one, longer video. I'll try to include a link to it in the description. Um, Here's the link to this video. Here's a short. God damn it. Okay, here's a short version of the link right here. Um, in case you want to pull up this same circuit. Okay, now, just for discussion of this, ignore that for the moment. Right here, you see this curve, is the voltage across the circuit. It's actually the voltage across the tank circuit, because this is an LC tank, inductive capacitive tank, fed by a DC signal with a switch on it. Now, prior to what you see here, I actually pressed this the switch over here, because here was the zero state before I hit the switch. Then right here I hit the switch, alright, and that basically made the voltage curve do this, the current through the inductor do this, and the current through the capacitor do this. Alright, so basically the current through the capacitor started at maximum, as all capacitors will do. If you take a discharged capacitor and stick a voltage across it, well, at the very first you're going to see the highest current that the capacitor will see, and then it diminishes up until the capacitor is fully charged. Okay, which is what we see here. When the current of the capacitor reaches zero, the voltage is max, so that's the maximum voltage it has across the capacitor. But remember, this is a transient state here, so this is not the operational state. This is right after I flip the switch, all this occurs. Now the inductor, on the other hand, has this current curve right here, so the inductor is starting to slowly charge its field, and it does that with ever increasing currents. Current starts at zero. Unlike the capacitor, its current starts at 100%. Okay, it starts at 0% on an inductor. The voltage across the capacitor and the inductor starts at zero, but because these two are in a tank circuit, you see the voltage increase, and that's because of the capacitor. But at some point, the capacitor is fully charged up to the level it's going to get to, but the inductor is still charging its field. So basically the capacitor's current starts going negative after a while, because it's actually starting to dump its energy into the inductor as the inductor is still continuing to charge. So once we get up to about here, the inductor is at 11.4 amps. Okay, whereas it should just be about 10 amps going through it, which is what it will have continuously. But right now it's at 11.5 amps, and that's because of that extra energy from the capacitor, which is still in the process of discharging. Which by the time we get about here, the capacitor, has basically dumped almost all of its charge, and it's the inductor is starting to discharge down to this, roughly 10 amp level, which is what you would expect given the fact you get a 10 volt with 1 ohm resistor in series with it. Well, that's going to produce a current of 10 amps. But at any rate, after all this stuff settles down, you end up with a situation where you have 0 volts, because the capacitor is completely discharged. All the capacitors, what little energy that capacitor got into it at first, was dumped into the inductor, which the inductor then eventually dumped it out of the system, basically. So it ends up stabilizing at like 10 amps, and there's no further oscillations or anything like you see here. But eventually, you know, when we get to this point, I actually open the switch. So when I actually open the switch, what happens is the inductor, you know, it's set here, the inductor had 10 amps flowing through it that whole time, kind of like you see over here. You know, if I, you know, let me reset this thing. So you can kind of see what's going on here. So the inductor, you know, has current flowing through it to the tune of, you know, by this point about 10 amps. So it's got, you can see what the little dots are. There's no dots flowing through a capacitor. It's got 0 voltage across it. You know, all the voltage is actually across the resistor, which down in this little area you can see what voltage is across the resistor there. You know, it's about almost 10 volts, but there's very little volts, if any, across the inductor at this point. And in fact, soon there will be no voltage across it. It's like 140 millivolts and falling. But that's how current flows, and that's, you know, the state we kind of see it in, you know, when you get to that other circuit. You know, it's like right here, you know, there's really not much going on. So, you know, it's roughly 10 amps at roughly 0 volts. But, you know, you have this current flowing constantly through it. This 10 amp current is flowing from our source, through the switch, down through the resistor, through the inductor, and then to ground. Okay. But like I said, that leaves us in, you know, over here for when I finally change the position of the switch. So which I can go ahead and do. I can open the switch and you see what instantly happens. Okay, so we see that now that the power source has been disconnected, see the current is still going through the same direction from the inductor through the capacitor, but it's actually charging it up. But the capacitor's current, you know, is now in a negative direction. It's negative 10 amps because that inductor wants to maintain that 10 amp current flowing through it, you know, that it had right here before we disconnected the switch. You know, it had a 10 amp current. Inductors want to try to keep that current flowing through it, and they'll generate any voltage across them necessary to try to maintain that current. And that's the key to understanding an inductor, is that it'll generate any voltage necessary to try to prevent the current going through it from changing. And that includes even if the inductor has 0 current on it. Well, you apply voltage across it, it'll generate whatever voltage it can to try to have no current flow through it. And you'll see that here in a little bit. But right now you can see everything's, you know, doing what it's doing. The overall voltage across the system is, you know, going more and more negative because we actually have a capacitor charging. The capacitor is not getting its charge from the voltage source, it's getting its energy from, exclusively from the inductor. Okay, so, you know, that's why, you know, damn that fucking mouse. You know, you can see kind of what's going on here for a little bit. You know, the current's still flowing the same direction, but the current is starting to decrease. You know, you can see that the rate of current, these dots are slowing down. You know, so, you know, because here's the current across the capacitor. Well, it's falling, but that's what a capacitor will do. Its current starts out really high when you switch it into charge mode, and its voltage will start out at 0, but its voltage starts to increase, and as that happens, its current falls off from maximum to a lower and lower value until it finally hits 0 when the capacitor is fully charged. An inductor is just the opposite. You know, here we're starting out, you know, in a state where it actually has, you know, a current flowing through it, by default that it doesn't want it to change. It doesn't want its current to change, but it has 0 voltage across it. But now that we've thrown the switch, it's becoming the source, so it's actually losing its energy to charge up the capacitor, because it's trying to do whatever it can to maintain that 10 amp current through it. Well, the capacitor, again, can't eat energy. An ideal capacitor does not dissipate energy, neither does an ideal inductor. It can only, in a tank circuit like this, they can only change it from one element to the other. So energy can go from the capacitor to the inductor, back to the capacitor, back to the inductor, etc. It goes back and forth. It oscillates. But anyway, as you see, the current decrease, well, the voltage you're seeing is actually voltage across the capacitor. Which right now is approaching negative 10 volts, because that inductor, if you recall, at first it had 0 volts across it, but the moment we disconnected that source, the voltage flipped from what it used to be, because it used to be a plus here and a minus here, but now you can see it's a minus here and a plus here. The inductor's voltage flipped so that it can try to pump, try to maintain that current flowing at that 10 amps. But again, it's less and less successful as it starts to run out of energy, but the inductor will continue generating a higher and higher voltage to try to charge this capacitor. Because like I said, an inductor will do whatever it can to try to maintain that current flow. It'll generate whatever voltage it needs to do to try to maintain that current flow, to try to stop it from changing. So in this case, since you've got a capacitor hooked into it, well, the capacitor across the voltage keeps increasing as it eats charge, okay, as it starts to charge up. But as a result, the inductor has to generate a slightly higher, an infinitesimally higher voltage than what the capacitor has across it. And it does that the whole time, right until it runs out of juice. It'll continue generating a slightly higher voltage even when it's got like negligible energy stored in it. It'll keep doing that and keep doing that up until it has no energy left. And when it has no energy left, that means the capacitor is fully charged. So, but again, the capacitor can't lose any energy while this is happening, because the inductor is generating a slightly higher voltage across the capacitor than it has at any one point in time. So instead of the capacitor losing energy, it's gaining energy, and only gaining energy. The only thing that's losing energy is the inductor during this first quarter cycle. Because what happens here, and you're going to see this in a second, that basically, in a periodic waveform like you're going to see here, because this basically we're turning a DC original voltage into an AC voltage, because what this is going to be is an AC waveform, like you see over here. It's going to turn into an AC waveform, because this is what we're basically headed for, in this simulation. So, this is the current across the capacitor, this is the current across the inductor, and that's the voltage. It's easier to see on this plot because I kind of dicked around with it a little bit to get it to come out this way. So the voltage, is, peaks at 10 volts. Okay, that's what we got applied. And the current peaks at plus and minus 10 amps. But the current and the capacitor and versus the current and the inductor are 180 degrees out of phase with each other, and they're 90 degrees out of phase with the voltage. So, basically the current leads the voltage in a capacitor, and it lags the voltage in an inductor. So that's why you kind of have the waveforms here, that you see. So, so basically, but basically, in this first cycle, the inductor is discharging, while the capacitor is charging up. And again, once the capacitor's current reaches 0, that means its voltage is peaked. Okay, that means the capacitor is fully charged, and because the voltage, the current of the inductor is 0, that means the inductor is fully discharged. And the same as the capacitor, it's got 0 current, so again, it's at 0 at 100% charge with a capacitor, because that's what you would expect with a capacitor. It has a voltage in it, but no current, it means it's charged. Whereas an inductor with no current means it's filled dead, because an inductor does not hold its energy unless there's a current flowing through it, so it has to actively be a current through it. Unlike a capacitor, which can, an ideal one will hold its energy forever. So, but inductor, you can't store that, without like a superconductor, or something, to maintain that current flow forever. But at any rate, the point is that these two components right here, the capacitor is fully charged and the inductor is fully discharged. Because the inductor has zero current, the capacitor also has zero current, so you know that it's the capacitor that holds all the energy right now. Now at that point, because remember what I was saying about the inductor generating whatever voltage it needed to try to maintain its current. It's trying to stop itself from losing current, but in the process that's leading to its own demise because it doesn't have unlimited energy to do it with. Well, at the point just before that this current inductor current goes to zero, it's still generating a voltage across the capacitor that's just infinitesimally and really small, but still greater than the voltage across the capacitor. But once it hits zero, that stops. I mean, the inductor is generating zero voltage now because it has no, just for a split second, you can think of it that way, it has no energy left in it, so it can't generate anything. However, again, like I said earlier, an inductor still, even if it's sitting at 0 amps, doesn't want its current to change. If it's got zero current through it, well, it wants to keep it that way. So what it does is almost instantly, once it hits zero, it actually generates a voltage across it that tries to oppose the capacitor. But now, instead of it generating a larger voltage across the capacitor, it's generating a slightly infinitesimally smaller voltage across the capacitor. The result is the capacitor starts losing charge because it continuously sees a slightly lower voltage across it, which means it's inclined to lose its charge. Okay, so for this next quarter cycle, what happens is the capacitor, discharges, and you can see that with the voltage, and you can see the current across the capacitor rises, again, in an opposite direction to last time, and so does the current across the inductor. It starts rising. Because why is it rising? Because it's taking energy from the capacitor now, so the energy is moving from the capacitor into the inductor. Okay, so the inductor's current is rising at the same time, so is the capacitor's current, because of the fact that the inductor wants to, as it charges up, wants to draw more and more current. And that's what basically is happening, is you got a capacitor dumping its charge into the inductor. And again, at some point, it's the current in the inductor, reaches its peak. So, because you can tell, that the current is maximum, okay, but the current, from the capacitor is actually maximum too. Because the thing is, the inductor is demanding a high current, right? That's what it takes to maintain its field. So the capacitor will try to supply a larger and larger current to that inductor because the inductor demands it. But at some point, when we reach this point here where the voltage is zero, that means the inductance is fully charged and the capacitor is actually fully discharged, even though there's a voltage on it now. So, I mean, there's zero voltage, but I mean, even though it effectively doesn't have any energy, its current, is still considered maximum. But now that the inductor, is up to full force, again, you had a really high current coming out of the capacitor towards the end of it, which again is the opposite of what you normally see in a charging capacitor. Normally see its current fall to zero, like we saw earlier. But here, it's the inductor that, since it's demanding a higher and higher current to try to, resist the, the increase, that capacitor is having to supply more and more current to it to try to discharge itself. So that's why you see the voltage eventually come down to 0. That means the capacitor's flat now, but the field in the inductor is fully charged now. So, the inductor is fully charged. Now it's time for the inductor to go back into a discharge cycle for the next quarter cycle. And it does, and as a result, right now, it's actually generating a higher voltage, across the capacitor than it has internally. So the capacitor is charging now again, but its current falls off, as it charges. So, and the current of the inductor, of course, falls off as it discharges, until finally, it reaches 0 at peak voltage. And again, since we got a peak voltage again, that means the capacitor is fully charged, okay, and the capacitor's current is 0, which is, again, is what you normally expect for a charging capacitor. Expect its current to fall, while its voltage rises. So, but now the capacitor has all the energy, so for the next quarter cycle, well, the energy is going to bleed out of the capacitor and start to charge the inductor again. So, you see the inductor current start to rise, and at the same time the capacitor current rises, because that's where the inductor current's coming from, is the capacitor current flowing in the opposite direction. So, yeah, these currents continue to increase as the voltage drops, since the voltage is dropping because the capacitor is discharging. So that's what you can kind of look at it as, as the voltage waveform actually indicates the charge level of a capacitor, even though the inductor is actually generating the voltage you're seeing, when the inductor is discharging. So when it's charging up the capacitor, the voltage is actually coming from the inductor. When the capacitor, like you see here, is charging the inductor, it's generating the voltage. It's, the capacitor is, like I said, when the voltage reaches 0, that means the inductor is fully charged, and like I said, you see the, the current's maximum. So, like I said, when the capacitor is charging up, its current increases and its voltage falls right up until it, runs out of juice, which means the inductor is fully charged at that point, which is peak current. And then, once the inductor is fully charged, then it goes back into a discharge cycle, and which starts out at the high current it left off at to try to, resist its current changing, but that ends up dumping all its energy eventually into that capacitor, and the cycle keeps repeating. So basically, every quarter cycle, of the waveform, a component will go from a charging phase to a discharging phase, and then back to a charging phase, and then back to a discharging phase, and so on, forever. So, that's, in some ways somewhat analogous to how light propagates, in the sense that you have a self-fulfilling waveform that travels through space, because you have a magnetic field kind of, supporting an electric field, and, but the currents are kind of out of phase like that. So, it's sort of like electromagnetic propagation in some ways. But at any rate, anyway, that's pretty much what, goes on in a resonant circuit, and why it resonates, and why, why these two aren't simultaneously charging, because they can't, because again, an inductor will override a capacitor's internal voltage while the inductor is charging up the capacitor. So that's why you see the voltage increase, but its current's falling off. But really, all you have to pay attention to is the inductor current and the capacitor voltage. So, and then once the voltage peaks, the current of the inductor reaches 0 and it's out of juice. Okay, but then, the capacitor is master at that point, so it's the source of voltage in the circuit, not the inductor anymore, and that's what basically charges up the inductor. It's, trying to resist its current increasing now, but in the process of resisting it, it's making its voltage slightly lower than the capacitor's voltage, so it's actually absorbing energy from the capacitor, and as long as that's happening, the capacitor can't do anything other than discharge itself. So the capacitor can't charge itself, it's the source of energy, and until it's fully out of energy, and that inductor and that field in the inductor stops changing, at that point the field in the inductor will start to collapse, and that's when again it'll start transferring its energy to the capacitor by putting a slightly higher voltage the whole time for the whole quarter cycle, across the capacitor than it naturally has built up already. It's infinitesimally smaller. But then once the voltage is peaked, and the inductor is out of juice, well then the capacitor is in charge, and it'll have a slightly higher voltage than the voltage the inductor generates across itself, trying to resist the change in current. So, that's, basically how this system works. So,